Thank you, Laura. Thank you for the nice introduction. It's a pleasure for me to be here today to introduce my course, actually. The title, as you can see here, is a little bit different. The title of my course is Optical Turbulence and Laser Beam Propagation. Of course, I cannot cover all these topics today, so I prefer to put a different title, a little bit more specific, because here the goal is give you a basic understanding of optical turbulence and focus on some main effect that optical turbulence induce on a laser beam. Okay, so anyway, I put here the outline, not of this presentation, but of my course. In red, you see the topic that today I, let's say, partially cover. And unfortunately, I don't have time to talk about what you see here in black. So today I'm going to talk about optical turbulence. How we model optical turbulence using a strata function power spectrum. I'm going to show you what kind of regime we can, a laser beam propagation to the atmosphere can face. We separate this regime as a weak, moderate, and strong. I'm going to show you a little bit what I mean with propagation laser beam through atmospheric turbulence, not time of oceanic today, but also oceanic turbulence is something that you can model, let's say, using this kind of approach. Okay, all these things, of course, you can, if you're interested, you have to go, you can see the details in my course. You can learn from there. I'm going to talk about effects caused by turbulence laser beams and images, such as scintillation, beam spread, beam wander. Then I'm going to give you an idea how we measure optical system performance and what is the impact of turbulence on this performance. Of course, they are deleterious. Turbulence is deleterious. And finally, just one slide on what I mean with non-Kolmogorov turbulence. Okay, but let's focus on a main question. So why do we need to deal with optical turbulence? I mean, optical turbulence is very complicated, right? You will see, required a lot of effort, mathematics, physics. So why we have to stress ourselves on that? The answer is simple. The answer is that optical turbulence, in particular atmospheric turbulence, is affect any kind of light or laser beam that go through the atmosphere itself. So we have many applications of this kind. We have, for example, free space laser communication. We have a satellite laser communication in the case of uplink and downlink, where the beam anyway have to go through the atmosphere. We have direct energy, so energy laser weapons, where the laser beam is propagating through the atmosphere. We have astronomical observation. This is actually where, you know, concept like scintillation, other stuff come from, right? When we were looking at the star, we have the problem that the star twinkle because of our blur, because we have the atmosphere. We have atmospheric turbulence. Application like laser radar, remote sensing, imaging. So as you can see, this is a topic of big interest in the field because can go through many applications. Okay, involve many applications. But what is atmospheric turbulence? Atmospheric optical turbulence in general. Optical turbulence is simple. I mean, is a fluctuation of the index of refraction. And why we have a fluctuation of the index of refraction? We have a fluctuation because we have a fluctuation of temperature. So in the air, in the atmosphere, but also in the ocean, or also in human tissue, for example, we have a fluctuation of temperature that induce a fluctuation of index of refraction. And then we have optical turbulence. In the specific of the atmosphere, we call it atmospheric turbulence. So as you can see here, for example, N0 is roughly 1 in the atmosphere, right? Is the refractive index, the mean value. And then we have a fluctuating part. This fluctuating part is random. So we need all the random process theory, random field theory in order to model this stuff, the atmospheric turbulence. So you see that this N1 is a random deviation from its mean value, a small fluctuation, but they are random. So we cannot use an approach that is deterministic. And also, the time variation in the refractive index are often suppressed in the treatment of optical wave propagation. Okay, so why, as I was telling you, turbulence is complicated. It's complicated because as a random nature, okay? Is basically random in space and time. And then we need to use a statistic approach, the theory of random process, random field, in order to model it. We need to use also all the parameters that are going to describe basically turbulence are random, so are a random variable, random process. And this makes things more complicated, of course, require also some strong approximation, and make also turbulent field a quite interesting topic because it's very challenging. So I hope that some of you is going to be interested and is working actually on this field, because still there are many other challenges that need to be faced and solved. So as I was saying, we need to focus on random refractive index, and we model the random refractive index with actually a strata function. We'll see later on what is a strata function power spectrum. So as you can see, basically, to summarize, random process, optics, and wave propagation, because then there is also the fact that a laser beam go through turbulence, so there is also the propagation aspect, is a mix of scientific field that have to converge in order to treat these things. Okay, so, but what is Kolmogorov turbulence? Kolmogorov, why Kolmogorov turbulence? Let's say that Kolmogorov was the first to introduce a power spectrum that is still used today. After more than 85 years, the Kolmogorov theory basically still applies. Most of the time it works. And Kolmogorov was so smart that was able to understand, let's say, in inertial range, you will see what is inertial range, the power law of the refractive index fluctuation is -11/3. This is a magic number there, a magic slope that most of the time works and in the inertial range. And I have to say it's quite, was really a smart find this. So we will see also that Kolmogorov sometimes fail, unfortunately. This brings some to the attention. We are also, that's why we are also interested in what we call a non-Kolmogorov turbulence, because sometimes you will see in the last slide, Kolmogorov doesn't work. But anyway, let's see now. I move. I don't understand why it's not moving. Maybe from here. Yes. Okay. Let's see now the energy cascade Richards theory. What is basically the Kolmogorov theory is based on Richardson theory. And what is it? Imagine now that we have the ground. Okay, ground, and then you have some energy injection, like coming from the sun, wind shear, convection, all these kind of energy that are going to build up the biggest cell of turbulence. We can visualize turbulence like many vortex in air, many optical vortex. And the biggest one, the inertial range, is called the outer scale. Then there is an energy transfer, until you reach inner scale. In inertial range, this energy is inertial, is transferred inertially, right? Then you reach the smaller scale, which is called the inner scale. And beyond that, you have only it, okay? So we start to visualize now these cells as a turbulence, but we have to model these cells. We have to deal with that. How we do? Well, let's associate to each of them a spatial wave number, spatial frequency, basically. You see, if we have the cells of different size, L1, L2, L3, we can define K1, K2, K3, like 2 pi over L1 and so on. So basically, we can represent in a Fourier space, you will see in a power spectrum space, all these sides, okay? So And what we do at the beginning? Well, first we have to start from a structure function. What is a structure function? Imagine that you have a specific volume, and you look at 2 points, and you look at as the fluctuation of index of refraction are correlated in these 2 points. Then you basically you see that you are calculating the structure function, and then you can do the Fourier transform in order to get the power spectrum. But to be more specific, the structure function here is basically a squared difference in 2 different points. You average over many realizations. The higher is the number, the better it is, usually 100, 500, 1000. And then you can, when you construct your structure function, because you do it for several distance r, you are able also to calculate the power spectrum. In the case of Kolmogorov turbulence, if we assume isotropy and homogeneity, that's a strong assumption of Kolmogorov, the structure function is this, where Cn square are 2/3. This is the typical three-dimensional structure function for Kolmogorov. Cn square is the structure constant, okay, which represents the strength of the turbulence. You see that in case of, as I said, homogeneity and isotropy, you can, your Fourier transform basically, well, a little bit more than Fourier transform, but anyway, basically it's a Fourier transform. You can look like this, and you can obtain the Kolmogorov power spectrum, which is this typical well-known power spectrum, 0.033 Cn square kappa minus 11/3. 11/3 is the magic power law that Kolmogorov was able to understand using a dimensional analysis, okay? And you see that is the range that that we are going to focus on in our calculation. So from the outer scale to inner scale, you have this different scale of different size turbulent cells, and outside of this range, of course, you have a different range, which is called, for example, energy dissipation range, for a scale smaller than the inner scale. But let's start now to look at the propagation aspect here. Most of you probably know this kind of formula. This is something that actually I downloaded on Wikipedia. It's a standard formula that describes how a Gaussian beam that is collimated at the transmitter evolves as it propagates. So you see, as you know, if it's collimated at the transmitter, it's going to diverge with an angle theta, a total angular spread given by this theta here, and then okay, we can define also the Rayleigh distance, blah blah blah. But what is the point here? That this is a specific case when your beam is collimated at the transmitter. But we want to be more general. We want to end up in case where also I can have a divergent beam, focused beam, and also collimated beam as this one. So what we do, we can introduce a random. We can introduce a wavefront radius of curve of the wavefront, F0. And you see that we can have 3 different cases. The case where F0 is lower than 0, then we have a divergent beam. The case where F0 is higher than 0, and then we have a convergent beam. And the case where F0 is infinite, and then of course we will end up in the previous case, which is a collimated beam. Okay, so we model this. Here, I try to put out all the formula. People that know me know that I put a lot of formula in my paper stuff. I don't want to stress you out on this. Here, I would like just that you catch the concept, the main concept. But here, I need just 2-3 slides where I have to put some formula, but not so hard, I promise. So this is a basic, actually, equation that describes the complex amplitude of a Gaussian beam. You know that we define the spot radius as basically W0. Then we have the phase radius of curve of the F0. We have K, which is 2 pi over lambda, which is the wave number, so the carrier basically radiation. And you see that these are the transmitter plane. If we go in the receiver plane, so basically at distance zeta equal to L, we obtain from Huygens Fresnel integral, the solution, give us this equation. In this equation now you see that this PL, which is usually called the propagation parameter, show 2 main coefficients. One is called 2 main parameters, sorry, theta 0, lambda 0. where theta 0 describe the amplitude change due to focusing, so describe basically the refraction parameter, is a refraction parameter, and lambda 0 describe the amplitude change due to diffraction. So it's basically a diffraction parameter, which is called also Fresnel, okay, parameter. Why this is nice? It's a quite powerful. It seems this theta lambda, sometimes people can get confused, but it's quite powerful because with this theta 0, lambda 0, you basically can characterize the geometry of your beam. Okay, for example, if you want to end up in a case of plane wave, I can set theta 0 equal to 1, lambda 0 equal to 0, because it means that basically W0 is infinite. So lambda 0 is 0, and F0, in that case, also, in this case, you have also theta 0 equal to 1, because you have F0 equal to infinite as well. So also you can characterize if you are in the far field and near field. But basically, what I mean here, why I would like to introduce this theta 0, lambda 0, actually it's something that was done from Andrews and Phillips. By the way, all the my course is based mostly on Andrews and Phillips, another publication that I made, but mostly on Andrews and Phillips' book. So you can see a couple of parameters, theta 0, lambda 0 at the transmitter, and a couple of parameters, theta lambda, which is related to the to theta 0, lambda 0. They are related to theta 0, lambda 0 by a conformal transform. Okay, so when you know this theta 0, lambda 0 at the transmitter, or lambda theta at the receiver, you know how to characterize the Gaussian beam at the transmitter of the receiver. So it's become quite powerful. For example, what about if I want to know what is the spot radius a receiver in zeta equal to L? Using this approach, theta 0, lambda 0, you can see that you can express, here we are talking about spot radius in free space, no turbulence. I didn't include any turbulence so far in this equation here, okay? So this is the spot radius at distance L, basically due only to diffraction in free space, okay? So you have W0, which is the spot size of the transmitter, and then you can express either way, using the transmitter parameter or the receiver parameter. If you look at the intensity, also you can get this expression here. But now let's focus on something that hopefully you can enjoy a little bit more, which is, okay, I have a beam. I have a beam that goes through the atmosphere. There is the atmospheric turbulence. And how this beam is affected? As I was telling you before, okay, first the case where we don't have turbulence. As you know, if you don't have turbulence, of course, we have only diffraction, and you get this diffraction limit red spot here. Okay, so your beam will look quite uniform. What happens now if there is turbulence? There are different cell sides. Each of them affect the beam in a different way. And how? The biggest one, so basically the cells that are bigger than the sides of your beam, are going to induce beam wander, and the smaller induce diffraction. So you have this combinational effect that play a big role. So as you can see here, I use the mouse, hopefully you can follow me. The red disk is the diffraction limited spot. Because you have further diffraction due to the smaller scale, you end up in the yellow spot, okay? But then you have also the cells that are bigger than your beam that are going to move your beam along the direction of propagation. So these yellow disks here are moving, randomly are moving, okay? And on the long-term period, you have a bigger spot where you can see this green circle here. So in the end, you're going to have, for example, spot sides, we call long-term beam spread, okay, which is now not only which is given by the spot radius that you have when you don't have turbulence, so only by diffraction, which are called the pupil here. Let me move here, otherwise I don't see. Okay, W pupil. I put pupil because here we are not in the focal plane. This is analysis on the, let's say, a distance L. And then we have this term T, okay? This term T that is basically related to turbulence. It's the spread due to turbulence. Okay, so I have to speed up a little bit, I guess. So the long-term B spread can be calculated if you use which is called, I don't have time today to talk about this, but usually we use with turbulence regime. We use what is called the Rytov method. And if you look on Andrew's book, but all these details are given also a little bit more in my course, you can calculate this T-term. If you use Kolmogorov power spectrum, you see that this T-term is given by 1.33 sigma r lambda phi over 6. So what is a sigma r? Is the Rytov variance, which is the scintillation index for plane wave. I will talk about it later a little bit. Okay, so basically what is this T? Is a parameter that describes the spread of your beam due to turbulence, and that's why I include a parameter, the Rytov variance, that is higher when you have higher turbulence, okay? And lambda, which is something that is related to the geometry of your beam. Okay, and this is a main parameter for a free space optical communication. Why? Because it is the parameter that is going to tell you how much power you are losing due to turbulence. Okay, now, okay, so if you look at the intensity, well, as we start with a beam that is Gaussian. In free space, we know that remain Gaussian. Is that true also in turbulence? I mean, the beam remains Gaussian, yes. This film showed also that it's quite good approximation that the beam remain Gaussian and the intensity look like this, where now you see that you have WLT, the long-term beam spread, here, that of course is bigger than your diffraction limited spot radius. Okay. The on-axis value of your intensity is basically given by this ratio here. Okay. This means basically also that the turbulence due to irradiance is completely determined if you know the W0 and WLT. W0 is something that you know because you know the spot size of the transmitter. If you are able with formula and the stuff that also show in my course to calculate WLT, but you can also, if you know how to use this formula here, you can calculate it with this formula. You are able to know also what is the on-axis intensity. Now, what I showed you before was at the pupil plane, as I say, at distance half of the transmitter. For practical application, like for example, free space optical communication, of course, your fiber or your sensor is located at the focal plane. So basically, I don't have time to show you this, but you can think of this in, you're going to get it, if you want to know the spot size on the focal plane after propagation in turbulence, the approach is very similar, I mean, but you have to use ABCD matrix formulation. There are details in this paper that I published on optical engineering last year, okay? And you can end up with a similar formula here, where now you have the spot size at the focal plane, and the T focal, which is a term related to the spread of turbulence, but on the focal plane. Okay, so, okay, I think I'm pretty much there as at the time. Let's now move on scintillation. What is a scintillation? Scintillation are spatial temporal fluctuation of intensity, okay? Here we are at the pupil plane. It is basically the variance of intensity scaled by the square of the mean intensity, mathematically, this is the formula, okay? Scintillation is affected at the most from turbulence cells of the Fresnel scale, which is given by square root L over K or square root lambda L, depends how you prefer to express it, okay? And as you can see, scintillation is a problem. Why? Well, because if you want to do, for example, optical communication, this fluctuation of intensity means that sometimes you have also dark zone across your beam, which means that you're going to blind your sensor. We will say this later. But let's try to understand the physics behind the scintillation, why that's happened in turbulence. Okay, think about a flat face, okay, here on the left. This flat face start, let's suppose you have a plane wave, started to, or you look at the middle of a huge Gaussian beam, whatever, you can approximate with a flat face, and this face started to propagate to turbulence, and you see that start to get aberrated. Then you see, if you think of it with the ray optics, that you have some rays that are diverging, others that are converging, so they are going to bring away sunlight or focus sunlight, and you get these different bright, different zone with different brightness. So you're going to end up with darker and brighter region. This region, of course, move random. Scintillation is a random process again. I mean, is moving randomly, and they require all this kind of statistic approach. That's why we use, you know, power spectrum, structure function, blah, blah, blah. Okay, so of course, I cannot go into details today. I'm sorry, but okay, what is the Rytov variance? As I say, Rytov variance is the scintillation index for plane wave. Okay, so the scintillation index for a plane wave, why is important? Because we have here two, how we can say that our beam is propagated through weak or strong turbulence. We cannot say that if we have only CN square, which is the information about how strong is the turbulence, or L, which is the length of the path. We need basically both of them, because maybe I have a very high CN square, but my beam is going to propagate a few centimeters, then in that case, I'm in the turbulent regime probably. Or the opposite case, when CN square is very, very high, very, very small. Let's suppose I'm, you know, at 10 kilometers of altitude, and I'm propagating my beam for many kilometers, but still probably I'm in with turbulent regime, because in this case, Rytov number is lower than 1. So basically, when you have Rytov number is used to distinguish the turbulent regime, and when it is lower than 1, it means that you can use a Rytov method and that you are in a weak turbulence regime. Okay, so here just to give you an idea about how the beam look like. You see that at 350 meters and a 5 kilometers, so they are two different distances, but down we have also, when we increase the value of the CN square, the strength of the turbulence. So you see, for example, in the bottom right, you have a beam that is totally broken, and you cannot do nothing. Of course, you cannot do optical communication with this beam, right? So, but let's say up to, you know, weak, moderate turbulence, we can quite succeed in our application. There is a method which is called the extended Rytov method to also, let's say, to extend the theory of Rytov, but this was done by Andrews and Phillips. But still, I mean, it's an empirical method that still need to be improved, let's say. So there is not too much we can do when we have very strong turbulence, because as I will say here in this plot, basically what happened that when a sigma r Rytov number, basically, when the Rytov variance is lower than 1, you are with turbulence. When you start to increase the strength of the turbulence, okay, or in this case is the square, so is sigma 1 here, is the square root, you increase the value, and then you see that there is a zone here called focusing regime, and then because multi-scattering start to play a role, your beam gets totally destroyed, you go to saturate, your scintillation is going to saturate to 1. Okay, so I go fast here because I would like to show you in these 10 minutes main application, which is free space optical communication. Why free space optical communication is interesting? Well, first for the bandwidth, because we have, as for the fiber, a bandwidth that use optical frequency, so is higher than in microwave. So we have higher data rate, can be deployed very quickly. Suppose you have a disaster recovery scenario where you have to go there, you put two telescopes, these two telescopes can look at each other, and then I can transmit information. I mean, you don't need to make, you know, to build like for the fiber and invest months and months of work, and you have to prepare where you have to put your fiber, whatever. So, and also easy, there is an easy integration in the fiber system because it's similar technology. So you can, for example, still use a 1.55 micrometer as a wavelet. There is no spectrum license required, and are narrow beam, right? A narrow beam, because the they are optical beams, are very narrow, and from the security point of view, this is a big benefit. So, but what are the problem here? The problem is that because the beam go through the atmosphere, we have optical turbulence, like I said, but also we have what is the main problem when it's present, which is fog. Because here we have also atmospheric turbulence is treated separately from scattering absorption. Okay, enter the question of budget leak separately, we will see later. But of course, when you have a situation where you have a 225 dB over kilometer of attenuation here, you cannot do free space optical communication. You have to maybe have a hybrid system or find a different path that with microwave that can succeed, let's say. So it's very important, but even what is why optical turbulence is of interest? Because even a clear day, clear sky day, turbulence is there. Is there is anyway need to be kept in count in order to build correctly your system. Okay, so what I would like that you see here, that basically I have a few slides to go. I think I'm on time. This is the well-known equation for budget link, right? When you want to build up a system, you have to receive a certain amount of power, the receiver. So you transmit a certain amount of power, you have to establish your trade-off of variable here. But what is important here, that where atmospheric turbulence enter this equation? Atmospheric turbulence enter this equation here, in the divergence of your beam, because it's going to spread more your beam. It's not going to enter here where alpha range here, this is the typical atmospheric attenuation. So you see there are two independent terms. The exponential one is that one due to, that usually you can calculate with Motran or other kind of software, you know, is due to scattering absorption. And here in the divergence, you have the dimension of your beam due to the threshold limit spread, but also turbulence. Okay, so how turbulence now impact, for example, a coherent system. As you know, a coherent system is a system where I transmit as a constellation of bits, and because of the atmosphere, you have scintillation. You see what happened to your constellation, the receiver is spread and moving. This means that there is higher the chance that you are going to make a mistake when you're going to decide what is the symbol. So you increase basically the symbol rate due to turbulence. Okay, because of turbulence, you increase the symbol rate. This is one effect. Okay, for this is what happened for a coherent system. But let's look at the free space optical system performance for direct detection system. We're going to look at probability of fade, signal to noise ratio, bit error rate, just a main concept. What is probability of fade? What is the fading? Fading is intensity drop at the receiver. So basically, let's suppose this is at the pupil. Let's suppose that the green circle here is not here, but is behind on your focal plane. And then you focus this beam on your focal plane, but you still have this kind of scintillation here that basically, you see that your sensor, I suppose, is going to be blind in some moment. So your intensity is going to drop. There are this yellow region here on the plot. The intensity is going to drop a given threshold, and then you lose information. This is the fade. Okay, very simple. Just a mathematical formula here, the signal to noise ratio. The signal to noise ratio without turbulence, as you know, is given by the RMS signal power over RMS noise power. Okay, in turbulence, first, you have to note the notation here. We have a bracket because these are basically random variable, okay? I mean, sorry, our average, mean value, our mean value. So we put a bracket there. And also is interesting to note that is going to be, even if you increase your signal, the power of your signal in principle to infinite, so your SNR 0, which is the signal to noise ratio without turbulence, to infinite, you see that the signal to noise ratio in turbulence is driven by scintillation. So you see here in this plot, if you plot signal to noise ratio in turbulence as a function of signal to noise ratio when you don't have turbulence, you have this line here, the 45-degree line, that is, of course, the ideal case. But when you start to increase the scintillation, this curve move away. So you have a penalty in terms of signal to noise ratio. Okay, on the bit error rate, this, I think I'm there. The bit error rate, same. When you have a sequence of bit 0, 1, okay, and you have a scintillation, you have also noise, you see that there are bits that you're going to lose. So you're going to lose a bit error rate due to scintillation, okay? And finally, I would like to spend a few words about non-Kolmogorov turbulence, also because probably most, maybe 99% of all my papers are on this topic, more than 50. It's a topic of interest because, as I say, sometimes Kolmogorov turbulence doesn't work. So we have to find, let's say, a different model that is able also to, let's say, describe a situation where we have a different power law from Kolmogorov, for example, or there are cases where the hypothesis of isotropy does not apply. For example, when you transmit a beam very close to the ground, you don't have a perfect mixing, you start to have some anisotropy, okay, anisotropic turbulence that is going to affect your beam in a different way. There is a paper that we published with Korokova in Miami, for example, where we measured anisotropy using intensity correlation over a field there, American football field. Okay, I think this is pretty much all. Unfortunately, there was not too much time. Hopefully, you have an idea about optical turbulence, and also if you are interested to know more deeply what a turbulence is, how it affects the beam, how it's modeled. You know, my course is about 8 hours, where I can is almost 200 slides, 180. So there is more time. You're free also to interact with me all the time. But this can do also it now. But hopefully I can see you in Orlando on April 15, and then see you there. Thank you for attention.
Thank you so much, Italo, for that fantastic presentation. You can tell that there's a lot of information to cover on this topic here. And as Italo has said, he covers so much more in his full-day course at the Defense and Commercial Sensing. So let's take some time here. We have about a little bit more than 15 minutes or so to address any questions from the audience. Again, if you have any questions, please put them in the Q&A box. And then we'll call your name if you include your name. And it looks like we've got a few questions here. The first one is from Jay Sethi. I apologize if I mispronounced your names, Jay. If you'd like to unmute your mic and ask Dr. Toselli your question.
Hey, thanks. Yeah, wonderful presentation, Dr. Toselli. Just what is the max attenuation do you see in laser comm or open space laser comm? Like how much of a loss are we talking about? Like 100% on a normal day, or I just want to understand what is the challenge like.
Yeah. Well, you mean attenuation due only to turbulence? Or
yeah. Atmospheric, yeah.
Yes, but again, for atmosphere, you have basically two kinds of attenuation. One due to the fact that the beam spread due to turbulence. Another one because you have absorption and scattering. If you suppose a clear day sky, now I don't remember, I have a plot on the presentation, I don't remember, I think it's a 2 dB, if the attenuation is 2 dB a kilometer or something, I don't remember. But this is only for the scattering absorption. From the optical turbulence point of view, depends how long is the path, how strong is the turbulence, what kind of aperture you have at the transmitter, all these things. Okay. So I cannot tell you exactly what is the loss that you have. But let's say usually you can have a power in, you can quantify this with also power in the bucket. And maybe you can get, I don't know, 40–50% power in the bucket in a good day with not too strong turbulence.
Wow.
Just to get I don't know.
Okay. So the second part of this question was, of course, I think the wave number also, well, it depends on the wavelength. So can we assume like if it's a higher wavelength?
Yes.
Okay. Okay.
Yes, of course, there is, if you look in the Lenny Andrews book, you look at this well-known formula of scintillation, for example, you have the K term that is always ahead of the equation. So this K term is 2 pi over lambda, which is the wavelength. It means that in microwave, you still have scintillation, but it's not so strong like in optical bandwidth, okay?
Yeah, okay, got it. Sorry, just the last one. Modulation. Does some sort of modulation still help with like getting more data across, even if you have a lot of scintillation? Like, can you use a lock-in amplifier or some FFT system to extract data, even if it's jumbled up with a lot of turbulence in between?
Well, there are many effective, many techniques in order to improve your performance, let's say. First, you have to keep, I didn't talk today about aperture averaging, so you can increase the aperture. If you talk about only modulation, of course, if you are able to do a coherent is better than, as you know, than you have a more bandwidth or whatever, you have more degree of freedom than direct detection. If you use a FEC, forward error code, they are going to help also. I mean, this here, that's what I said before, is very interesting that this kind of field, free space optical communication, is a relatively new field, but can also take from the fiber optics field all the technology, all the techniques in order to, from the modulation point of view, for example, in order to, you know, to also to be effective, let's say, more effective. Of course, here the situation is different. You are not in the fiber, the medium is different. But I would say there are so many aspects to consider that it's hard to answer with only you know, one basic phrase, because here it depends what kind of beam. I talk about only Gaussian beam, but there are so many exotic beam that you can use that can be improve performance, multi-aperture. I mean, many things that are there in the lecture that you can take a look. And it's hard for me to tell you what is the best, to be honest.
Right, and I guess this book that you were using throughout the presentation is the best resource to go find some stuff on.
The book Laser Beam Propagation through Random Media was published in 2006 by Andrews and Phillips, the second edition.
Okay.
6, 7, or 5. But then there is also another version. So I, let's say, spent most of my time as a science on that book. So I know very well the book, I can recommend. But I don't want to be, let's say, there are many good books in the field. Also, Sasiela book it look quite with a big formalism. All these books are published by SPIE, by the way, by SPIE. So the formalism seems quite strong, but when you manage it, it's quite powerful because, let's say, it's more engineering oriented. You can also build up some, you know, you can apply that the optics, other stuff, filter function. So I recommend, as a science, I don't recommend a book. I recommend to study several books. But of course, you're going to have your book that you like the most.
Right, thank you.
But yes, these all these very good. If you are somebody that is in the field, I would have on my shelf for sure Andrews and Phillips book. As I would have Tataschio other book, I guess, but where they also older one, but they are good book, I guess.
Right, thanks. I'm just giving a little bit of background. I'm just starting in this. I'm coming from a mechanical engineering background, so any direction is really appreciated. Thank you so much.
You're welcome. And very usual could be also the field of guide of Lenny Andrews, which is a small book with all this formula, maybe to put in your pocket can be useful. Don't be lost in the mathematics, because in this book there is a lot of mathematics. Try to understand the main concept. That's why it's important also to read paper, read the several books, read as a different book, say the same things in a different way, because you don't need to be focused only in the mathematical, then you have to know the core of what you're looking.
Right, thank you.
You're welcome.
Thank you so much for your question, Jay. Thank you, Dr. Toselli. We've got quite a few more questions coming in, so I'm going to move right along here. It looks like I apologize for any name if I say your name incorrectly. Justus Burskis. If you'd like to unmute your mic and ask Dr. Toselli your question.
Hello. So thanks for the presentation. I was also wondering about, like, many times I hear about Gaussian beam and so on, but basically we also have some more interesting light structures. It's Bessel beam, which has this elongated profile and does not diverge so much. Also, it is robust to some turbulence, to my knowledge. Like, was any investigation done on this topic, and like, how would you see the influence of such light structures on the field, on basically?
No, there are many papers actually coming out also this day by, for example, Forbes from South Africa, that these people work on structured light. And yeah, there are what we call, some people call also exotic beam. There are these kind of beam that have, seems to have a better performance. Sometimes they are self-healing or they spread less. So it depends. Also, if you look also many Olga Korokova papers, she multi-Gaussian, there are several kind of investigation. But to be honest, I think it really depends on what kind of system you need to build up and how much you are going to complicate your life when you don't use a Gaussian beam, because everything for Gaussian beam is pretty much, at least with turbulence, calculated. So you have your expression there, you can calculate your spot size. And in the other way, you have to go more maybe through chaotic simulation, which is also works, but maybe take longer, non-analytically. And also you need probably also to generate this beam, to manage this kind of beam that require probably more expensive technology. So really depend from what you need, but of course they are very promising.
Thank you.
Welcome.
Thank you so much. We have another question here from Ian Wallhead. Ian, if you'd like to unmute your mic, there's a couple of questions there from Ian.
Hello, can you hear me?
Yes, you sound great.
Yes.
Okay. One question I have is regarding the CN squared value. It's well, one question is, what's the typical value of this? It obviously varies with the level of turbulence, and is it a fixed? Is it a constant then, or is it wavelength dependent?
Okay. There is a slight dependence from the wavelength, but this is neglectable. At least this is neglectable. If you look how CN square derived from CT square, you have to look on the theory of this. But CN square is considered a constant, usually 10^-14, 10^-13. Let's say a strong value start to be 10^12, 10^13. 10^14 is what is a standard clear sky day, what you get ground level. The more you go up in altitude, of course, the atmosphere become less dense, then you start to reduce also the value of your CN square. So there is, for example, Ufna Valley profile, which is a well-known profile used in academia, which of course need to be improved. The people are working to improve it, to make it more precise, but there you can have an idea how the CN square evolve, change, let's say, with altitude. But a typical standard value that you use this value in this model ground level is about, I guess, 1.7, 10^-14 meter to -2/3. This is the a standard value, yes.
And a second question. Obviously, turbulence has a detrimental effect to the propagation of the beam. How does it compare with atmospheric scattering? Would you consider it worse, or in general? This is really
in general, I would say if you are in a clear sky day or slightly foggy day, then you have to be worried also about turbulence. If you are in a very you start to have a quite good fog, I don't think you care more about turbulence, because of course when scattering absorption are going to dominate a lot, and Actually, you have to see if you're able to be successful with your link in this case. For example, also in ocean, to give you an idea, in oceanic turbulence, in the ocean, also we have turbulence. We have a fluctuation of temperature and then fluctuation in the refraction. We call oceanic turbulence. But in the ocean, you cannot go behind the 50, hopefully 100 meters one day, because your scattering becomes devastating. So I would say turbulence count, to consider turbulence is important, but of course is less relevant when you are in very scattering environment.
Okay, thanks.
You're welcome.
Thanks for your question, Ian. So we have about 5 minutes left, and we have a few questions left, a couple of people here. Francesco Nardo, if you'd like to unmute your mic and ask your questions, and then after that we have one more in the Q&A, so if we can try to get it wrapped up in about 5 minutes here. Hi, Francesco, are you able to unmute your mic?
Unmute. Yep. Can you hear me now? So sorry. I simply have two questions. You can just answer in simple words. That's what I really need. The first one is, what is the difference between the modified von Karman spectrum and the Kolmogorov power spectrum? Why is the first one
modified,
preferred? Or in which scenario is the first one?
If I remember well, this is the beginning of Andrew's book. The modified include also you have basically this spectrum include a roll-off, you know, in the inner scale and outer scale, let's say the buoyancy range and what is called a dissipation range. So basically for the modified, if I remember well, you have inner scale and outer scale. Okay, you introduce an exponential where you have, you include the effect of inner scale and you include an inner scale and outer scale. That one that is not modified, unfortunately, I don't have another book. Maybe there is only one of them, but there is not a big difference. I mean, also there, it depends on why you need to use the spectrum, because most of the time, what I did, for example, for the calculation long-term spread that I showed you before, the T term I showed you before, if you look through the slide, there you need to use a spectrum that is not Kolmogorov, because Kolmogorov diverge. So you have to introduce you have to use the von Karman spectrum. But when I think about von Karman, I usually think that one that includes both inner scale and outer scale. I'm not so worried if it's modified or not modified. I mean, there is otherwise there is a other spectrum that describes better a bump near the inner scale, which is the Andrews spectrum, for example, or sometimes people use a different one. But here the main concept is that when you don't use Kolmogorov, usually you are introducing also, you're keeping count also in a scale, outer scale. And this sometimes, because as exponential, is going to help to solve the integral. So from the mathematical point of view, sometimes when you have a singularity on Kolmogorov, it's better if you use this kind of spectrum, because you also sometimes can make your integral converge. Okay. So it's more a mathematical, let's say, concept than because to be honest, also the von Karman is not really physical if you think about that. It's a way, is an artifact that we found in order to make this roll off mathematically, but in practice we have we should be only in the inertial range in this kind of hypothesis, because there is isotropy, there is homogeneity.
Yeah. I mean, that was my problem. You have 4 or 5 different power spectrum and you have to pick one. And for me, the easier, the better, no? And really, and that was my question. Or if you have a preferred one, if I should.
The preferred one is that one that I use most in my paper. If you see, is the, again, it depends from what kind of parameter you have to use. If you have to calculate scintillation, then maybe I will use only Kolmogorov, unless you need the information like what is the input outer scale or inner scale of my scintillation that I'm calculating, okay? Then you have to use von Karman. But it depends what you need. If you need to know how outer scale, for example, impact on your beam wonder, which is usually quite remarkable because outer scale impact on beam wonder, then you have to use a spectrum that include outer scale. You cannot include you cannot use, for example, the Kolmogorov.